Hello everyone and welcome to my channel. Hope you all are doing well. In our previous video we had a brief introduction about this subject, and now today we'll be starting with the basic level. As I already told you, that is the finite state machine, or some even call it as finite automata or FSM. Okay, now first of all let's have a look at the formal definition of finite automata or FSM. So it is defined as a machine which takes discrete inputs, gives discrete outputs, and has some internal configuration. These internal configurations are also called as internal states or simply states. So finite automata is one of the simplest model of computation. It is basically represented by 5 tuples or characters. So it's also called as a 5 tuple machine. So it is represented as M equal to Q, sigma, Q naught, F and delta, where M is the machine or finite automata, and these are the 5 characters which represents this machine. So let's try to understand these 5 characters one by one. So first we have Q. Q is a finite non-empty set of states. So what are these states? They are the, as I already told you, these are the internal configurations, or you can also consider them to be the levels. Okay, a state is represented by a circle, and inside the circle we have the name of the state. For example, here I am writing Q1, so Q1 is the name of this state. Fine. So Q is represented as Q0, Q1, Q2, Q3, Q4 up to so on up to Qn. The number of states depends upon the machine. For example, in certain machine we can have Q equal to Q0 and Q1, only 2 states to represent that machine. In another case we can have Q equal to Q0, Q1, Q2, 3 states to represent this particular machine. Okay, so this is all about states. Now next we have another tuple, that is the alphabet, which is represented by means of sigma. Sigma is a set of symbols. Now you'll be like, what are these symbols? Set of input symbols. Okay, so what are these symbols now? A symbol is anything like A, B, C, or it can be like 0, 1. It can even be a character like 5. Okay, it's just an symbol is just used to represent certain entity. Okay, so input symbols are one which can be given as an input to the machine. For example, we have a machine that takes binary strings as an input. So for that, sigma will be equal to 0, 1, because these are the 2 binary digits. Fine. Now for a machine which takes the input as vowels, for that we can have sigma equal to A, E, I, O, U. So now we saw what these symbols are. Now the question is, what are these symbols? What are these symbols used for? So from these symbols we can make the strings. Say for example we have sigma equal to 0, 1. So the possible strings that we can make out of this are 0, 0, 0 or 0, 1, 0, or it can be like 1, 1, 1, or anything that just contains zeros and ones. Similarly, for example, we have sigma equal to A, B. For that the possible strings can be AA, BB, ABA, etc. See here, the strings only contains those symbols that are present in our sigma. Okay, now let's move on to the next tuple, that is Q0. Here we have Q0. Q0 is one of the states which belongs to Q that we already mentioned. Fine. So it is one of the special states and is also called as an initial state. All the processing of the strings that we feed to the machine starts from this initial state. It is represented by an arrow coming out of nowhere pointing towards a state. So this is the representation of a initial state, and inside this, as you already know, inside this we have the name of state. For example, here we write Q dot. So Q naught is the initial state. You have to remember one thing, that we have only one initial state in our finite automata. Fine. So the next tuple that we have is F. F is the set of final states. Again, these states are the ones that are present in the set Q. So we can say F is the subset of Q. And we can have, and here like we have only one initial state, but we can have more than one final states. Okay, they can be more than one final states. Fine. So the question is, how are we supposed to know which state is the final state? So the final state is represented by a double circle. Like a state, we have, for a state we have a single circle. Normal state we have a single circle. For initial state we have an arrow pointing towards this single circle. But for final state, it is represented as a circle surrounded by another circle. So this is the representation of a final state, and again inside it we have the name of the state. Now let's see the significance of this state. Okay, this final state. Fine. So on processing a string, for example, we have a string ABA. On processing this string, we start the processing from starting character and we end it at the last character. Okay, now if the processing of this string stops at one of the states that are present in F, then we say that the string will be accepted. Okay, we can say string will be accepted. But in case the processing stops at one of the states that are not present in F, we'll say that the string will be rejected. Fine. I hope it is clear to you. Even if it is not clear right now, you will understand it in the next videos when we'll just try to solve some examples. For time being, let's just keep it like this, and now let's just go through the last character that we have, that is delta. So delta is also called as a transition function or a mapping function. It is represented as Q cross sigma gives Q. Now you'll be like, what is this? This is very simple to understand. See, here it simply means that when an input symbol from sigma is applied to the state Q, it shows a transition from the present state to the another state, or simply you can say that it moves from one state to another state, or simply it can be another state or the same state. We represent the transition function by means of transition graph or transition table, or you can use both of them to represent a particular machine, particular finite automata. See, we all have seen graphs. So graphs are just what are graphs? Graph is just a collection of nodes and edges. So these nodes, for example, we have the nodes like this. These nodes represent the states, and these edges, this is a directed graph. These edges represent the transition from one state to another state. And here a self loop, it represents a transition from the state to the state itself. Okay, in case of finite automata, these nodes represent the states, these edges represent the transitions. Now let's I'll just randomly try to draw a graph over here, so that you'll be able to understand what a transition graph may look like. Fine. So we have we'll just take an example. We take three states like A, we'll take state B, and we'll take state C. Now finite automata has a initial state, so let's make it as our initial state. It has a final state as well. Let's just take C as the final state, and now we'll draw some transitions from one state to another. Say these are the transition, these edges show the transition from one state to another state. I'm just randomly trying to draw this graph so that you'll understand what a transition graph for a particular machine may look like. Okay, so this represents a machine which has initial state, which has final state, which has transitions, and on these edges we mention the symbols that are present in sigma. For example, here we have symbols AB. So over these edges we'll write down like A, B, A, B, A, B. Now for time being, let's forget about A, B, what these transitions are, what is meant by this arrow going from A to B. Let's just have a look at this diagram. Simply this represents a particular machine. Okay, we'll in our next video we'll try to analyze this graph and dot down the 5 tuples that we already mentioned. Till then, take care of yourself, and do like and share this video, and also subscribe to my channel to remain updated. Thanks for watching. See you in the next video.